There you go. All right, so those are the points. Those are the points on the right-hand side of x squared. Using the symmetry, then we should also know that we have negative 1, 1, we have negative 2, 4, and we have negative 3, 9. And if we connect those with a smooth curve, there's our x squared. Correct? Okay. Now, the reason I put that one on there is because that one is going to be the foundation for how we find all of these other ones. Okay? If we look at x squared plus 5, okay, all that's going to happen, and I'm going to color these points. How can I do this? I want to go back to. There we go.
And like you literally just walk around one from last night at Water World, really shaky, and I hated it.
You don't walk out by yourself, do you?
Oh no.
Good.
My mom picks me up every day.
Okay.
So.
Good. All right, so we've got that graph right there. That's x squared, right? Now, if I look at x squared plus 5, all I want to be able to do here is realize what, if these are the points for x squared, okay, what does x squared plus 5 look like? And why? Yeah. Why do you just move them up 5? Okay, good. So if I look at the equation, this I think gets overlooked a lot of times. If my equation is y equals x squared plus 5, this is saying y is whatever x squared's y was plus 5 more. So if I had 1, 1, then I should have what point should show up then on x squared plus 5? If 1, 1 showed up, 1, 1 plus 5 should show up. So that works out to be 1, 6, right? Okay. So I should be able to do the same thing for 2, 4. So 2, 4, and then plus 5 to the 4, right? So 2, 9. I should be able to go 3, 9, and then plus 5 there, right? I should be able to go 0, 0, but plus 5 to the y value of 0. And I get those. Okay, and that gives me K, H, I, and J, right? Is my axis of symmetry still that line right there, the y-axis? So then this value of H, this ordered pair of H, I should also have negative 1, comma 6. This one here should be, it's 2, 9, it should turn into negative 2, 9. This one should be 3, 14, turns into negative 3, 14. So when we graph y equals x squared plus 5, you see that all that happened is that these points that were on x squared, every one of them increased in the y direction by 5. Is that okay with everybody? Okay. So that is a relationship, guys, that is very important for us so that we don't waste time graphing something. Because I would really hate us to sit, or hate for us to sit and create a separate chart for question number 2, and then create a separate chart for question number 3, and a separate chart for question number 4 from scratch. Does that make sense? Because we know what x squared looks like, we should at least be able to have the starting point to get to the other one. So what I mean by that, if I know, and basically what I'm trying to get you guys to commit to memory, is if I have x and f of x, where f of x or y is equal to x squared, we should have a handful of 5 points that we've memorized. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Those are 5 points off of x squared that we should commit to memory and know that they exist all the time. Does that make sense? So then if I want, let's do question number 3. If I want y equals x squared minus 3, then what do I do with all of these y values? Just subtract 3 from them. And I get 4 minus 3 is 1. 1 minus 3 is negative 2. 0 minus 3 is negative 3. 1 minus 3 is negative 2. And then 4 minus 3 is 1. So if I plot the points, negative 2, 1, negative 1, negative 2, 0, negative 3, 1, negative 2, and 2, 1, does that give me all the points I need to graph x squared minus 3? Is this okay with everybody? Okay. So x squared minus 4 would be subtracting 4 from there, so I won't graph that one for you. Let's go to the back. The back was a little bit different because we have negative x squared. Okay, so negative x squared should look if we create our table again. So if y equals negative x squared, let's just choose some x's and y's real quick. If I choose x to be, let's just say negative 2, and I plug that in here. So what we've got, remember, order of operations are important here. So you're going to have the negative that's out in front, and now x became negative 2, and you'll square that. What's negative 2 squared? What's negative 2 times negative 2? Positive 4, right? But you've already got this negative out front there. So it takes that positive 4 and makes it negative 4. And if I try the same thing with negative 1, negative 1 times negative 1 is positive 1. But the negative out front makes it a negative 1. 0. So we'll have something like this. 0 squared, 0. Opposite of 0 is just 0. Try then 1. So if I try 1 squared, I get 1. Take the opposite of it, you get negative 1, right? Yeah. The same thing's going to happen for 2, then it's going to give me negative 4. So if I plot those, negative 2, negative 4, negative 1, negative 1, 0, 0, 1, negative 1, 2, negative 4. You get your parabola, but now it's upside down, right? And we call that concave down. But now if I want to go ahead and like add 4 to that, like the question number 6 says. If I'm going to add 4, that means all you have to do is add 4 there, add 4 there, 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 and there, right? So if I do that, we're going to have negative 2, 0 will be a point. Negative 1, 3 will be a point. 0, 4. 1, 3. And 2, 0. And does that look like negative x squared plus 4? Is that okay with everybody? So remember, and I just want to make sure we understand this. This is telling me what is happening to the y. Y is whatever you knew negative x squared to be, but then add 4 to that. Okay? And we should be able to then, if I want to go, so I'll just give you all of these real quick for the remaining parts of that worksheet. Negative x squared minus 3. And then negative x squared plus 1. Should look like those for 7 and 8. Is that something we can feel somewhat comfortable with? Okay. All of these are of the form. All of them are of the form. Oh, didn't want to do that. of y equals ax squared plus c. Now we haven't dealt with that a too much. So all of these were that a was a 1. If we look at the a, what that does in comparison to just x squared,
Is there a way that you can like make that graph bigger without it making like the numbers bigger, so to say? Does that make sense? Like for it not to be infinity, I should say. You get what I'm saying?
like this, like
Yeah, to zoom out but be able to see the end of it.
right. So you're never so I can do. It goes up to like this, so I can. So you see those numbers. I mean, I'm zoomed out pretty far. So right now, this number is 18 million. Okay, and you're seeing that things keep going on, right?
Allow me that now.
So it will never, like, you're never going to be able to get to, because it goes on forever. So you're never going to get to an ending point. And at some point, like, I keep doing this, I keep zooming out, but there will be some point in which GeoGebra kind of runs out of computing power to give me any more. But the idea is, no matter what you choose for x, if I choose a very, very, very large number for x, you can always square it and get something even bigger, right? So you're always going to get some y value that's bigger. Talking about that a number out in front, all that a number does is, we call it a vertical stretch. But what's happening is, if I look at this point right there and compare it to that point right there. So let's color code this stuff. So the red stuff and then the blue stuff. So the blue point, okay, you see at these 2 points, they relate to one another a little bit. Okay, this is the point on the blue curve, this is the point on the red curve. But this number right here, this y value, is twice as big as that y value, isn't it? Does that make sense? And it's twice as big because of that 2 that is on this red curve's equation compared to the 1 that's on the blue curve's equation. If I make that a value 3, and now look at keeping the x values the same at 1 and 1. Now do you see that the y value is 3 times as bigger? Or 3 times as much? If I go to x being 2, let's say x is 2 on both of these. So if x is 2, you get 4 back on x squared. But if x is 2 on 3x squared, do you see how that 3 and that 4 and 12, how they compare? This 12 is 3 times as big as that 4. And it's because of that number right there. That's the differentiating feature between those two graphs. Here it's a 1, there it's a 3. So that a out front, all it does is basically what we say is it stretches the y values. It makes them however many times bigger. So in this case, 3 times bigger, or if we go 4 times bigger, or whatever. Yes?
So are you going to send more people in tonight, or are you just going to wait until the
We'll talk about it in a little bit. Questions on this? We okay with these? So my hope at this point, before we move on, is that we are comfortable with, shut up, with what y equals ax squared looks like, okay, where we've got the vertex at 0, 0, the axis of symmetry at x equals 0, okay. We've got y equals ax squared plus c, where that vertex is going to be at 0, comma, whatever c was. And the axis of symmetry is still at x equals 0. Okay, those are the 2 types of graphs that we've talked about. Okay. Now on there is also some. I asked you to find the y-intercepts and x-intercepts. The y-intercept is where you cross the y-axis. Okay, so all of these were either basically the y-intercept on all of these would have been the vertex. Okay, x-intercept is where you cross the x-axis, and that's going to be stuff that I don't want to spend a lot of time talking about right now in that worksheet because it is going to be information that we spend quite a bit more time on here in the next couple days.